Welcome. This is the warm season spotter course hosted by the National Weather Service office in Burlington, Vermont. My name is Seth Kudikoff and I will be sharing this talk with you all this afternoon. So we'll get started with an overview of what will be covered. This presentation will cover quite a bit of ground, going over what Skywarn is and what it means for us. Talk briefly about what we do here in the Burlington office. We'll talk about the science of thunderstorm development and the forecasting process, what the Storm Prediction Center does for us, and how we collaborate on convective watches, all the storm types and convective warnings that we issue here in the local forecast office, and then the important safety and reporting for severe weather that you all can do for us. And we will start now with the overview of Skywarn. So Skywarn has been around since the 1960s. It's a national network. And of course, at the local level, we have our weather spotters help us out in reporting what's going on in our community for severe weather. And this, of course, includes the warm season and the cold season. We'll have you trained in part by processes like this, where we provide some educational material, and there are other places as well where you can also get more information and be ready to give accurate reports for us. And of course, the Skywarm program has its roots in amateur radio, although nowadays plenty of people outside of that community can help out with storm reports. So basically, the people who are our storm spotters range basically from the general public to all sorts of folks who have interest in weather information, from emergency management officials to the media to our research community. All rely on spotter information, and the reports that we share are valuable for a large community of folks across the United States. And as you know, this is a volunteer program, so it is completely free, and we just ask that you are trained by a process such as this, where you are getting a spotter talk in a virtual setting, and hopefully we will be able to be in person very soon. We encourage you, of course, to be in touch with us here in the Burlington office, and we rely on some information, of course, where you are located, and this, of course, you can give us storm reports from your location, even if it's not at your residence. And of course, spotters are needed because we simply do not have technological tools to see everything that is happening when it comes to severe weather. So in this example of the radar imagery here, depending on the distance from our radars, you will overshoot. Basically, the radar is not seeing anything near the ground as you get farther from the radar and as the elevation angle increases. And so therefore, especially in northeastern Vermont, as this example shows, you are likely to, as a radar operator, you're likely to miss what is happening near the ground, even if the signal is for thunderstorms well above the ground. It doesn't necessarily translate to the surface. So that's a big reason why we need our storm spotters. And so our spotters, as I mentioned in terms of the radar, the observation is not near the ground, and the spotters can see that. And so their reports are quite valuable, and sometimes they even directly lead to a severe thunderstorm warning, where we, as forecasters, will indicate that, for instance, hail of quarter size was observed as opposed to as radar indicated. And in terms of winter time, we also make use of our spotters in terms of updating our forecast. In this example here, it shows that in the model world, in the forecasting, as forecasters, we see a signal for heavy snowfall. And we don't know exactly how heavy that snowfall is. This is a probability of heavy snowfall of an inch per hour. However, a storm spotter was able to indicate to us that they were seeing 3 inches per hour. And so that indicated to us that we would have actually much heavier snowfall amounts than that were indicated by our previous forecast, and therefore we were able to update the public with the best information we could possibly provide. And in this particular event from last winter, these were the snowfall amounts in central and eastern Vermont that were larger than what we initially had expected. So again, the translation from the forecast office to our products. Overview of the National Weather Service. So we are part of over 100 forecast offices across the country with the mission to provide weather, water, and climate data for the protection of life and property. So that is our #1 goal, is to prevent any undue harm to, as part of the Department of Commerce, it's keeping the economy going and of course saving lives related to weather, water, and climate dependent events. Here in Burlington, Vermont, we of course are focused on most of Vermont and northern New York, and this means our forecast area is prone to quite a bit of variability throughout the year in terms of weather events, partially due to our topography, which is highlighted in this map. So of course we have various mountainous areas and hilly sections of eastern Vermont and wide valleys in the St. Lawrence Valley, Champlain Valley, and into the Connecticut River Valley. And so a lot of these features play a large role in terms of the hydrology and in terms of the severity of both in terms of how our warm season, what we see in terms of areas that are prone to maybe see more thunderstorm activity or severe weather, and in terms of flooding. So we, of course, are, as a entity, we are a 24/7 operation, so we are able to day and night be able to provide the latest weather information, and we are simultaneously working on improving our forecasts as we put them out. So we are improving our forecast through various technology and research to get our forecast as accurate as possible. We of course rely on spotters and other public volunteers to flush out our observational network. So we use a lot of that data. So in terms of the frequency, for instance, of hail, location of wind events, basically all that data can be used in research projects to better understand what areas are basically what is conducive to severe weather, for instance, for our area. So before I move on to the next section of this talk, this is an opportunity to ask any questions related to the National Weather Service and Skywarm.
I have a question. You can hear me?
Yes.
Just curious. I recall that you used to be located at the Burlington Airport. Am I correct? You've since relocated to downtown Burlington? And how has that affected or changed anything about your weather service office?
So that's interesting. Actually, that was planned, but it never actually occurred. So we actually still are in the Burlington Airport.
I'm glad to hear that. And I'm also delighted to know as a pilot that you're about to add Northeast Kingdom Airport as a new TAF location.
Indeed, we are excited to offer that service next month. All right, thank you. Okay, if there are no further questions, we'll move on. So we have this acronym ACES that is used by the Skywarn community that stands for Awareness, Communication, Escape Routes, and Safety Zones. Basically, the bottom line is that your safety is always number one, and therefore we want to make sure that in situations of severe weather that you know what to do, basically. And so the types of hazard will dictate what you should be doing in terms of situational awareness. So this slide demonstrates basically 5 key hazards. And so thankfully, we do not see the first 2 very often, the tornado and large hail. But if you do have a tornado warning or a severe thunderstorm warning, in these situations, you certainly need to move away from windows and get into an interior space. You don't want to be outdoors at all, have any risk of your bodily harm. Of course, the structural damage is inevitable in those type of events. For severe wind, it's fairly similar idea, of course, being out of harm's way, knowing where to be in those cases. Flooding is tricky, of course, because that can be something that starts off not looking like too big a deal, and suddenly you're moving into waterways that are quite dangerous, especially if you are in a vehicle. And lightning is a tricky hazard as well, because that can strike pretty unexpectedly if you're not paying close enough attention. So we'll start with the flooding idea, just as an overview. Obviously, it's going to be dictated by heavy rainfall. And so we know that the flash flooding is particularly likely in areas that are populated and with concrete, and basically when water is not able to run off, you see rapid rises in that water. And to get an overview of just how scary the force of water can be, this demonstrates here this little picture of just a small amount of water can, up to when you get to 6 inches of depth, if it's moving quickly, it can knock you out, and once it gets deeper than that, then vehicles also can be swept away. So very dangerous, of course. Don't underestimate the power of water. Similarly, for lightning, it can be quite dangerous. This cloud to ground lightning in particular, and we do have a 30-30 rule that basically is along the lines of the first 30 means that if it takes less than 30 seconds to hear thunder after seeing a lightning flash, that basically means lightning is within roughly 5 or 6 miles of you, and so it's probably close enough to pose a threat. And then the second 30 in that 30-30 is referring to 30 minutes, in about how long before you can resume outdoor activities safely after a storm ends. So of course, the power of the lightning, that electricity, means that you may be in danger if you are using electronic devices. So you'll want to stay away, of course, from water or tall trees, or metal objects. It's all related to the tremendous amount of electricity that comes from lightning. So the best place to be, of course, is in a interior location that is sturdy. Indoors for lightning. And we'll move on to another hazard that I haven't mentioned yet, and that is heat. So heat safety is important, of course. We are going into the warmer season. Last year we got some hot weather by the end of May. Hopefully this year it doesn't come in so early. But heat index is something we measure as a combination of temperature and humidity. We, at the forecast office in Burlington, have criteria for heat advisories and excessive heat warnings based off of the heat index. Typically we'll issue heat advisories, and in rare instances we'll issue an excessive heat warning when the heat index may exceed 105 over at least a 2-hour period. And so in either case, depending on your activity level and your health, you may see symptoms of heat exhaustion or heat stroke. So we certainly recommend paying attention to the heat index and monitoring those conditions during the heat of the day when we have those products out, and recommend getting to a cool air-conditioned place during those hours as much as possible. So we'll move on into thunderstorms. So on the basic level, we need to see a combination of moisture, atmospheric instability, and some kind of forcing mechanism. To become a severe storm, we need wind shear. So the small scale details we'll discuss later on in this presentation. But generally, the more organized the thunderstorm, the greater the severe threat. So the ingredients shown in a map form, the moisture often can come from the Gulf of Mexico and Atlantic Ocean. On the large scale, we see heating from the sun, and a lifting mechanism can be a cold front. And so putting those ingredients together, of course, is what we need to see some thunderstorm activity. And thunderstorm activity can lead to severe weather. And that severe weather is monitored by the National Weather Service Storm Prediction Center, which is in Norman, Oklahoma. And so we coordinate with that office to get the best watch information out to the public. So the idea of high impact hazardous weather is the key. So the SPC Storm Prediction Center is the entity that puts out products like this that you can see on their website that highlights across the United States for a particular day where severe weather is expected. And so this is done with a combination of model data and human analysis, basically a pattern recognition and seeing all the data that goes into the severe weather potential. And that potential can be scaled basically on a 1 to 5, which is shown here, where basically both the combination of how widespread the severe weather is expected to be and how intense the severe weather is expected to be is this scale works on those two categories. And typically up here in the North Country, we will be somewhere in the 1 to 3. The 4 and 5 is thankfully typically something that is not seen in our area, but certainly anytime you see anything between a 1 and a 3, that is something to pay attention to. And here's an example about 10 years ago of an outlook that included a slight risk, level 2, up into northern New York and the Champlain Valley of Vermont. And here is some more information to show some more detail into what the hazards are. So it's great to know that there's a risk of severe weather, but it's also useful to know what type of severe weather. So the SPC will break up into tornado, wind, and hail, and the potential hazard level for each of those may be different depending on the event. And as I mentioned before, we work with the SPC here in the forecast office in Burlington. The process basically goes from them to us, and we collaborate, and then it goes back to them to issue a watch. So they do the watches and we do the warnings. And so in this case, you can see two different watch examples for our area and for a different part of the country. So they basically will be formatted the same way, where it highlights the counties that are in the watch. And again, when it comes to the forecast office, we put out the warnings once the watch is already out, and so the warnings are on a smaller scale than the watch. So to demonstrate the difference between a watch and warning for severe versus tornado, it's a little tricky, because you can have tornadoes even if they're just a severe thunderstorm watch, but it means that there is a higher potential for tornadoes if you have that watch for tornadoes as opposed to severe thunderstorms. And the watch process is basically something that occurs, generally you could see it in the maybe 6 to 12 hour range before an event, and the warning is something that actually is imminent within a half hour or less typically. And to reiterate what the difference between a watch and warning, there are many ways to look at it. Some folks may prefer a taco watch and taco warning. Here at the Burlington office, we do the cupcake watch and cupcake warnings. So basically, we're putting the ingredients out for a watch. They're all here, but it hasn't been assembled yet. So once you created that cupcake, you can actually, it's there, ready to, it's actually here. So just because you have the ingredients doesn't mean you're going to have the actual cupcake. And so again, the severe thunderstorm watch makes you ready for severe weather, but it does not mean it's actually going to happen, and that's what the warnings are for. Before we move on, this is another opportunity for questions.
Since you mentioned tornado, just curious, is it correct the small tornado that occurred near Middlebury in March was the first time ever on record history for March? And B, was there a warning in effect when that occurred, or is that just a very unusual event?
Good questions. Okay, so to answer A, technically there was one previous tornado in the 1950s in the month of March. We are actively looking at potentially changing the categorization of that based off of some newspaper evidence of reporting that particular tornado. We have reason to believe it may not have been a tornado, but we are not certain yet. So as of now, it looks like it's the second tornado in March, but it's possible it may be the first on record. And that particular storm did not have a tornado warning. This is an example of where we had a severe thunderstorm warning for that area for that particular time. So in that case, we were not explicitly forecasting a tornado, but we did have a severe thunderstorm warning.
If you ultimately do not classify it as a tornado, would you consider it a microburst?
So microburst, that's a good question. The type of, if we didn't have an indication of rotation, that would have been the type of wind damage from that. It very well could have been. Okay, so we'll move on to the details of what warning criteria is for our severe weather in the North Country and across the United States. It's the same criteria we use for various severe weather. To start with hail, we need to see 1 inch diameter or larger to consider it severe. So that's equivalent to a quarter size or larger is considered a severe thunderstorm when it comes to hail. For wind, we need to see 58 mile per hour or greater. So essentially, the lowest end severe weather typically will have a warning for potential for 60 miles per hour or greater is what we will indicate. And so that is strong enough to actually cause significant damage. And therefore, we will not typically have any severe thunderstorm warning if it's below that threshold. Although you can, of course, see wind damage even if it's not at that level. Tornadoes of any intensity are, and as brought up with the Middlebury tornado, it's any kind of tornado, even a weak one, is definitely a severe thunderstorm. For lightning, interestingly enough, lightning is dangerous, but we do not actually put warnings out for lightning by itself. And for flash flooding, we have flash flood warning for areas basically if you have rapidly moving water in areas that should not see rapidly moving water, such as roads. So
I think I took everything upstairs.
So when
I
it
missed something, but I don't believe.
comes to the threshold for wind, it's something that of course cannot be measured if you're just looking at or feeling the wind, but you can roughly estimate the wind speed through this type of breakdown in basically a threshold of where you start to see actual trees that are moved significantly. That kind of gives you a guide of where it's severe level. If you just see branches falling off trees, typically that's sub-severe. So that's an example of, in terms of something to think about reporting strong winds for what may or may not be at a severe level. So here's an example of a polygon that we will put out for a severe thunderstorm and highlighting those hazards. In this case, we have the wind hazard, meaning that severe criteria where we expect 60 mile per hour winds. But the hail, we expect penny size, so that's sub-severe in this case, but it is something that we are highlighting as a potential impact. And again, for severe thunderstorm warning in general, it actually, as shown in that Middlebury case, you could still see a tornado even if it is not explicitly forecast. When it comes to our flash flood warnings, the polygon idea is going to be very similar. It can be drawn out in a very similar fashion, and the impacts are of course very different, so we will highlight those. And in this case, we have call to actions to avoid walking or driving through flood waters and to immediately move to higher ground. If you are in the path of this polygon, where in this case the potential is not only there, but it actually has been occurring somewhere in this polygon where water had been rising rapidly and there is flash flooding. So in our area, because of topography, it is challenging for us to pinpoint exactly where you will see this flash flooding. Certain areas will be more prone to it near, as I mentioned before, urban areas will tend to see flash flooding more than rural, and you also may see it more often in low-lying wetland area as well, especially if you're seeing in an area with steep terrain where water will flow rapidly from a higher level. Here's an example of a tornado warning for our area that was issued back in 2014. Thankfully, as I mentioned before, the strong tornadoes are not likely here. We have not seen any above an EF2. And even an EF1 and EF2 we know can cause tremendous damage. So these are something that we are very focused on in terms of research and making sure we can do our best to warn on these events. When it comes to the time of year, it's dictated by basically the more heating we get, the better chance we can sustain any kind of severe weather. So as we get to the warmer season, we peak in July, and things trend back down as we move into the early fall. So again, it's dictated by how warm we get to most, because that helps us become unstable in the atmosphere. We also tend to see more moisture, and we do continue to get frontal boundaries, which will help in terms of getting air to lift and get the thunderstorm process going. For particular hazards, we've done analysis to show what type of time of day and for what type of hazard we need to be most in tune with. So for wind, typically you'll want to pay attention to the afternoon and evening hours. Between 1 and 10 p.m. is when we see by far the most severe weather. When it comes to hail, it's pretty similar. This is a distribution of severe hail, and so maybe a little bit later and maybe a little bit earlier it peaks. So more of the mid-afternoon hours for hail. And then for tornadoes, which are less frequent, so it's not as many reports, but a similar distribution also occurs, where tornadoes are really, they're possible anytime, but in our part of the country, they are certainly more likely, again, between 1 p.m. and 10 p.m. In terms of location, we do see interesting patterns. So for hail, we will get reports clustered around more populated areas. And so highlighting here, Burlington, Middlebury, Rutland, so the Champlain Valley certainly, and into the western slopes of the Greens, we do see concentration of hail reports around roads and where people live. For wind, it's not quite as clustered. For wind, the analysis going back to 1955 shows a more even distribution across our area. To some degree, it's still dictated by the population, of course, but and that's why you see a cluster around Burlington, Vermont. And there tends to be stronger winds through the valley location, including the St. Lawrence Valley. Severe wind is more common. And then tornadoes, which are quite rare, of course. This highlights the rarity, just seeing how few pass over about a 66-year period, and there's really no discernible pattern with it, with such a few number having occurred. And generally speaking, the nature of tornadoes being a near surface feature mean that they're disrupted by the terrain, and so one likely limitation really is that when they do form, you can see that they don't last very long, even relative to average, and there is some tendency to move in a north-south fashion along the valley, basically following the terrain. So that's an overview of our convective warnings. If there are any questions about them, feel free. Okay, we'll move on then. So now we're going to discuss the types of thunderstorms. We'll begin with the simple cell, the simple single cell. This is often considered just a pop-up or garden variety thunderstorm. They typically will not create any severe weather, but they can be quite photogenic, as in this case. They're driven by the afternoon heating in a conditionally unstable environment. So basically there is air rising with enough moisture to condense, and we get the updrafts, and the downdraft that may occur is going to produce, it could produce heavy rain, and basically something we saw just last night in part of northern New York and northern Vermont. It briefly can create some lightning if the cloud height is high enough and the cell is just strong enough that it will be able to have development of lightning in the cloud. And here's an example of what they look like on radar. So it could look pretty impressive with the reflectivity, seeing those oranges and reds, but there's no real development beyond that. When it comes to what it looks like and as it develops, just the idea of its growth over time, and it generally will do so in a relatively fast manner, but also will dissipate relatively quickly as well. And the idea of having an anvil or overshooting top, that is an indication that you actually could see a stronger storm than just the garden variety, because that means the updraft is so strong that you're getting the precipitation processes are up in a high enough where you're going to see potential for mixing down some really strong air. Basically, the wind is in the downdraft potential is stronger with the vertical motions. You can see damaging wind and maybe even some small hail when you see the anvil. Here the related type of, when we're talking about wind, what can happen. So just as a brief overview of what strong winds can produce in terms of the going in a linear fashion, and rather than what a tornado has rotation, this microburst, which was mentioned earlier, and this is the idea that the strong winds associated with this of a cell can go out into basically, if they're strong enough, you'd have a persistent strong wind signature that can blow over trees if they're strong enough, and it's all facing basically a single direction. And we have seen this example from about 16 years ago in our area. It is something that needs to be detected very quickly, because the fact that this microburst, by its very nature of being on a small scale, it needs to be detected quickly in order to properly warn on it. So in this example, on the right hand side, it shows the velocity signature that shows in green the movement towards the radar, and in red away from the radar, which means that the wind is that there's an actual spreading out of wind along that line where that storm is. So corresponds with that single cell that you can see on the left hand side. So the single cell, again, it typically is garden variety, but it can, if it's strong enough, it can produce a pretty impressive wind signature that can become quite dangerous. If you see those anvil overshooting tops, then you could see a downburst signature or a microburst with strong winds associated with that. The next type of storm is a multicell. These are more common, and we certainly will see them frequently during the summer as single cells merge together. And we even saw a little bit of that on a small scale last night, where we had, ahead of a cold front, we saw a boundary that basically areas that the wind were calm, and then suddenly along a gust front. As rain moved in, we saw some gusty winds along a very linear feature. So just a basically a west to east moving line that is associated with the temperature difference between the head of that precipitation and the rain-cooled air in the downdraft of a storm. And so these storms also can be severe, and all hazards are possible, especially wind and hail, and rain as well. So often you see backbuilding of thunderstorms with the multicell features. And so the training of thunderstorms results in heavy rain over the same area. When we see multicell, that is something that we need to be paying attention to, and something that you can look at on radar. Here's an example of a gust front on the lower part of the radar image. You can see the very low light, the blue. The blue is basically on the southern flank here, kind of in an arc that illustrates that not associated with necessarily the heavy rain that is to the north, but you can, out in front, you can see gusty winds along that boundary. The next type of system as we ramp up in terms of potential damage is the squall line. So this is very organized now, this feature. So the squall line on the left and the quasi-linear convective system on the right produce similar features in terms of the impacts are primarily strong winds and heavy rain over a short period of time. The main difference, though, with the system on the right, the quasi-linear convective system, they can produce more likely, can have spin-ups of rotation. And in this relatively rare case shown here, it actually produced brief tornadoes. So the squall line is something that has developed for sure over our area. In this example, this loop illustrates the multicell becoming a squall line right over our forecast area, moving through the Champlain Valley, through the Green Mound into eastern Vermont, sustaining itself. So typically, because of how organized the squall line is, it will survive the terrain. And here's a little bit more on the squall line in terms of some of the cloud features you may see, with this example nearby in Colchester, Vermont. This shelf cloud indicating that there is some vertical rotation where you see large gradient basically in from the left to the right basically. So there's no horizontal rotation, it's vertically rotating, and there's potential for damaging wind and very heavy rain on the left-hand side of the image. As pictorially, you can see where the leading edge of the gust front, it shows up pretty well in this image on the left. This diagram of how you get this warm inflow into the storm, and this density difference with the warm air rising above the cold air, you tend to see this rising motion and pretty intense, a sharp gradient where you can get those really intense winds to come down into that, come down through that downdraft. So we actually saw this more recently here at the airport, which is shown here from last May, a beautiful shelf cloud. And here's some of the damage that you can, this is a clear example of strong winds in this picture here that were due to a squall line and the straight line wind damage that results from it. Finally, if we want to look at the most intense type of storm or wind damage, thankfully it is quite rare, but it's a derecho. derecho produces much stronger winds than even a squall line, sometimes well over 100 miles per hour. This is a rarity in our part of the country. It did affect portions of central Vermont. Back in 1995, this derecho has shown the track of it from northwest to southeast, basically. It typically will move very quickly, and that storm motion helps enhance the winds associated with the derecho. So that the main difference again is these winds are much stronger than for even a squall line, and the extent of those strong winds you can see here in this example. I covered basically all of southern New England into portions of Vermont and New Hampshire as well. So very large extent. When these happen, they are something that is remembered quite vividly for people. So hopefully we won't see them, as this shows here, the climatology, they are quite rare. Maybe 1 in every 40 years, and that might be on the high side for northern Vermont and northern New York. And just as a demonstration of what it looks like on radar, not terribly different looking than a squall line, in the sense that it's a very linear feature. This one is showing it passing pretty close to our focus area through Albany, New York. So this feature is just will produce quite strong winds that moves rapidly from west to east. Then we will move into the final type of storm, and that's the supercell. So the supercell is known for its hook echo, which wraps around. You can look at it from basically in a counterclockwise way, as this image shows. The radar reflectivity on the upper part is wrapping around counterclockwise into that debris ball signature. So as you may know, the radar is detecting any hydrometeors, not necessarily just rain, but anything that is detected that had a corresponding value of power that we receive at the radar. It doesn't necessarily have to be rain or hail. It can be debris, and that picked up by a tornado, and that's what is shown here. So this is actually not precipitation in that area. And so the mesocyclone, it's known as this circulation, and it's so as opposed to larger cyclonic system, this is of course a very small scale feature. So typically, if there is a tornado associated with that supercell, its width is just maybe a few hundred yards we're talking about. So that doesn't mean it can't affect a very large area, but at that pinpoint scale, this supercell, where we see this on radar, it is a very small feature for sure, and the rotation is its key point. Again, it's known as a mesocyclone. It's cyclonic. It's moving horizontally very rapidly, and therefore it is quite a photogenic feature. Of course, as an example here from out in the plain states, it can make it particularly easy to see all of its features with the flat terrain, and it typically is quite a tall storm. It does not ensure a tornado just because you have a supercell by any means, with only about 1 in 5 producing a tornado. By their nature, they are pretty transient. They don't necessarily stay at that. They don't continue. They don't persist at a very long period of time. So on average, maybe 20 minutes, and at the worst case scenario, up to an hour if the environment is just right. when it comes to that large, basically this cumulonimbus that is associated with all severe weather, you'll see formation of hail in the cloud. And so this demonstrates how the hail develops in that updraft. You'll get basically there's supercooled water that is going to interact with graupel. So the graupel is going to grow into hail. That hail can basically, as it gets heavy enough, it's going to fall. And when it does so, it can sometimes be lifted back up. And if it goes into the more the updraft dominant air on the right hand side in this picture. So basically this process is considered a recirculation of hail, and that allows it to grow. And if it grows large enough, that means on its way down it will not melt as much, especially if the downdraft is strong enough, or if that freezing level is closer to the ground, then there's less time to melt basically for the hail stones. So typically the large hail is going to be in an environment where those updrafts are very strong, and so the hail is able to grow quite large before coming down to the ground. And we do detect the hail on radar, and we do have signatures that we have studied basically to determine the difference between hail and rain, even though they both will show up on radar very clearly. They do look different, and we have different ways to use our radar information to compare basically it could be a mixture of rain and hail, or large hail or small hail. Different sizes of hail look different to the radar. And when it comes to another place where we see severe weather, we'll just quickly touch on tropical cyclones. Tropical cyclones last year affected our area, which was pretty unusual. We had a couple of those move through. And so these warm rain processes result in small drops of rain and high rainfall rates. So if you were experiencing the remnants of Isaias last summer, you may recall some of that type of rain where it was very small drops, which is notably different than what we get for severe weather in the for any other type of heavy rain scenario. And we do want to highlight that for our area it's unlikely, but a landfalling tropical cyclone can produce isolated tornadoes and also can cause wind damage. So this is one last part of our storm types for severe weather. To summarize, this chart highlights the differences in terms of what type of severe weather is likely or possible for the different cell types. So recall that the single cell can have strong winds and flooding and hail, but the key thing is that the severe potential is relatively low for a single cell. For multicell, you can have all sorts of severe weather, but also not particularly dangerous relative to the squall line when it comes to wind. The wind damage is something we highlight for if you see a squall line. Supercell, they're by far the most dangerous. They will produce violent downdrafts and large hail, and they may produce tornadoes. And tropical cyclones, again, unlikely to produce severe weather for our area, but if they do, we can see some strong winds and flooding. As a guide for our hail, just to go over what we see in our area, occasionally you do have large hail at the severe level, which again is that 1 inch criteria. Here, this picture actually shows a recent hailstone collection basically to compare to the quarter size, demonstrating just how large this large hail is. And this was from a supercell, and so again, you can see supercells in our area, and the environment doesn't have to be actually that warm and humid. In this case, if the air temperature is only 60 degrees. So we'll have to always pay attention to a lot of environmental information, not just the temperature and dew point, in order to see what potential there is for severe weather. And even bigger hail has been seen as well in our area. The largest hailstone we have recorded actually was not far away in Westford, Vermont. And this is measured here, 3¼ inch diameter. And to remember diameter, as opposed to any other dimension, as you can see in this picture, as with any large hailstone, it will look irregular. So the recommendation is to measure from tip to tip, and in this case, roughly, you could argue that depending on how you orient that hailstone, it would actually be a little bit shorter of a distance. So we like to see the picture whenever you report hail, because of how irregular the hail size, the hail shape may be. And of course, the potential for it to melt and shrink from its original size. There is a tendency to underreport hail size, partially due to how hail tends to melt relatively quickly. So for that section of the talk for our thunderstorm types and hail, are there any questions? Okay, nothing heard. We'll move on to a little more detail about tornadoes.
Excuse me, I was on mute. Could I just
Of course.
come in quickly with a couple of questions? Thanks for backing up. Just curious again, in the Northeast Kingdom, over the Greens, and in kind of a unique weather spot, I'm just curious, when you have a squall line, generally moving from west to east, but not always, and of course I understand there are a lot of ingredients that have to do with various stages of the life of the storm, but in general, do the Green Mountains, as these storms or squall lines move across them, tend to increase or decrease or affect the storm building or dissipating in any way?
It's a great question. I'm not aware of local research specifically on the intensity of squall lines that as they move off the Green Mountains. I would think that because of how well structured they are, that there would likely be, on average, little change in their intensity, but there could be an argument for basically a tendency for an increase in wind speeds associated with the movement. Basically, you're enhancing the combination of the forward motion of that line with the downslope wind off of the greens. It could lead to potentially some increase in wind speeds.
That would be my experience from years of watching them roll. Also, when they come directly up the flatter terrain from the north into the Northeast Kingdom and northern Vermont, they could be pretty incredible. Last question related to thunderstorms has to do with your radar. Am I correct that your radar is located in Colchester?
Yes.
And A, and B, the next nearest one that would relate particularly to northern Vermont and the Northeast Kingdom is in Gray, Maine. So we sort of see a composite. Of course, there's so many resources on the web these days. It's pretty amazing to watch the weather in real time. But am I correct that due to mountain and the visibility, that particularly lower visibility scans that's where it's coming from. But it doesn't really see everything because of the blockage of mountains on both the east and west side. Is that correct? Or
Absolutely.
are you only more concerned, or are you only more concerned about seeing a higher level? End of question.
Yes, absolutely. You got the nailed. So yeah, I touched on that early on, the idea that we rely on spotters in part due to the not only the elevation angle away from the radar, but because of the topography. Yep, as you said, the mountains are blocking those lower scans, and so when we see something that looks impressive, well, both we can see something that looks impressive many thousand feet above the ground and not know what's below it, but we also may have a situation where the feature is near the ground and not high up, and therefore the radar is completely missing it.
Thank you. I'll hold on to my last few questions for the end.
All right, sounds good. Thank you. So this is quite a stark photo here. Thankfully, again, this is something out in the Midwest and not here, but this is an example of a rotating funnel. And so once a funnel reaches the ground, that's when it is actually a tornado. So that's always something that needs to be emphasized. It can't be emphasized enough, is that funnel cloud is not the same as a tornado. The tornado on the ground is what we are talking about. So as you probably know, they are rare in our forecast area, and that's why they are big news when they happen, like the Middlebury tornado. And it's very easy to see something that, again, looks like a funnel, and it is not actually a tornado, and it may not even be a rotating funnel. In this case, it's actually, you would need to see it in motion, but the idea that something like this feature in the middle of the picture has that funnel-like appearance, but if it's not rotating, it's not a funnel. So basically, just that we want to emphasize that anyone who is reporting to us, we really want to make sure you can describe what you're seeing. And if you are not seeing rotation in a situation like this, then it doesn't really help us at all, because there's nothing dangerous about something like this. But it's always good to be careful. And here's another example of something that looks really scary potentially, but it's just a kind of a trick of the eye. It's just rain, and the way that some light is hitting it, it kind of looks more significant than it actually is. So more about tornadoes themselves, we'll again move our way from less severe to more severe. So starting with the weak tornadoes, even though they're weak, they are not actually weak when it comes to the wind speeds. So they're considered weak just because, by comparison to the stronger tornadoes, the wind speeds have a pretty low maximum. In this case, if you go up to EF1, we're talking about up to 109 miles per hour. They also tend to be small, and they tend to be the ones that we see in the North Country. And again, because they're relatively weak, thankfully they do not have as much impact as those stronger tornadoes. In fact, for tornado fatalities, they make up less than 5%. And yet they make up 80% of all tornadoes. When we move into the strong tornadoes, or the EF2 and EF3, these make up the vast majority of the remaining tornadoes and produce less than 30% of tornado deaths, and tend to be more sustained. So they, with their larger scale, they tend to cover more distance and produce wind speeds at a much higher, up to 167 mile per hour wind speed. And then the violent tornado is the one that is of most concern, because they produce by far the most fatalities. And thankfully, they are quite rare, making up only 1% of all tornadoes. again, just going off of the strong tornadoes, the trend continues, where as they get stronger, they tend to last longer, and they tend to cover more ground with wind speeds as high as 234 miles per hour, they're estimated. So we'll look at briefly what tornadoes look like in our neck of the woods, going off of the March Middlebury tornado. So you may have seen overview of this tornado that is on our website. This is one of the pictures that was shared of an attached garage that was moved about 10 feet from its foundation. So this was an example of EF1 level damage. This is just one little piece of a puzzle that we try to solve when we get reports of a possible tornado. And so we're kind of detectives. We put the pieces together from reports, and we need to see how it all fits together with spatial representation of where the storm path was and where it was not. So the idea that there needs to be corroborative evidence, basically, this alone is not good enough in terms of creating an actual path of the tornado, because we got this particular tornado affected multiple properties and multiple basically there's damage to tree, as you can see with this picture as well. There was an uprooted tree in the vicinity as well. So anyway, reconstructing the path based off of the damage results in a report such as this, where we have the EF0 level in blue and the EF1 in green, basically highlighting the path based off of the storm reports, the radar data we have. It's all put together to give the public the most accurate information as we can. It also is useful for research, for the media, and for insurance purposes as well, to have this type of information out there. So again, this was an EF1 that certainly produced damage to property and caused a couple injuries as well. So not a great thing to have, and it's certainly something that we want people to be aware of, that they are possible, and be prepared. And in this case, we did have a severe thunderstorm warning out for the storm, and hope that that message is heard. So that's all for tornadoes. If you have any questions about them, feel free to ask right now.
Yeah.
Hi, just a quick question about water spouts. Are they just tornadoes over the water?
Water spouts or tornadoes over the water. Roughly speaking, I'm not 100% sure the formal definition, but they are, I believe they are essentially the same process. Yes. Yep.
Question regarding Middlebury event. Did you all on radar pick up rotation from that as it was happening or recorded?
That's a good question. I'm trying to remember. I was not on operations. We, in real time, I wouldn't be able to tell you for sure. So those type of spin-ups, it was actually described in our in the report in our write-up about the storm. It's a type of spin-up that occurs between scans, basically. So unfortunately, when they're that fast, I believe in real time, that particular rotating storm, I don't believe we were able to see ahead of the actual tornado occurring. So it was seen, I believe, in real time, but the pre-warning we were not able to do that with the frequency of scans relative to how quickly that the tornado spun up.
And therefore, it might have occurred below your scan ability, too low. Is that possible?
No. So in this case, Middlebury, the distance from the radar, it did allow us to see it. It's just that the scanning process is we do increase the frequency to some degree of how fast, how many scans in a certain amount of time that we see at that low elevation, but it's still not quite fast enough. I believe that was the issue more than the elevation angle.
Thank you.
Okay, if there are no more questions, we'll move on to flooding. So similar to when I talked about the severe thunderstorm watch and the severe thunderstorm warning, we have the flood watch and flood warning that represent conditions being favorable for flooding and if flooding is actually happening. So we make sure to have that message out there that you're being prepared when there's a flood watch and you're taking action when there's a flood warning. And so the flood warning will only happen when a river system or so we're focused on that in terms of an example of something that should be in balance and where we're not seeing any runoff. Basically, the river rising to the point where we see widespread flooding is when the river is in balance. And so rainfall is only one factor. It's a key factor, but it's only one factor in terms of adding water to this. I mean, it could be a lake or any body of water, basically, that is in a certain level of balance that typically is disturbed by heavy rainfall. But as it shows in this diagram, it is also dependent on how much water is leaving. That basically it can depend on, for instance, if the soil conditions have been really dry, for instance. That's an example of something where you can soak in water if it's a steady rainfall and the infiltration, therefore, is on the high side. But if you have recently been seeing a lot of wet conditions and then we get heavy rainfall, that's where we're alerted to rapid rise of water, and that results in flash flooding. Right now, for instance, our river systems are on the low side, so we would need to see a lot of steady rainfall to get to the point where we even have to be concerned about that process occurring, where we have a gradual flooding system where rainfall is exceeding the rate of stream flow and the water level can rise to the point where we see widespread flooding. So that, again, can happen quickly or slowly, and it tends to happen faster in an urban environment, and that is due to the fact that water is not able to curve around, basically the fact that you have water that is not able to go, I mean, you're seeing water that follows a straight line that is not able to run off, drain properly, and you just have an accumulation of water where it should not be. And so this is an example of flash flooding in the summer of 2012. And we do monitor the amount of water that is needed to cause flooding. This is quite variable across our forecast area due to factors such as urbanization and due to topography, where the higher terrain typically can see higher rainfall rates without seeing this type of flooding. So again, the flash flood is what we're most interested in because it happens so quickly, and that is something we are concerned about and have seen across Vermont. In the worst case scenarios, we see scenes like this with just tremendous amounts of water over roadways, and the gradual rise of water is still of importance, but for most of us, the flash flood is something that we are most in tune with in terms of the impacts to society. So the climatological nature of flood is somewhat similar to severe weather, but we also have the complication of the spring snowmelt. So in a typical year, not like this year, but in most years we see a lot of snowmelt and ice jam situations that result from the thawing of our frozen rivers, and so that's why you see a spike in March. Otherwise, flooding is typical in the summer months, and there generally is less in the way of flooding in the fall, where we see more runoff and less ponding of water. The particular patterns that result in flooding for us, we do see, and of course we did see about 10 years ago, the impact of a landfalling remnants of a hurricane with Hurricane Irene in an environment that was already quite wet. So the preconditions of wet ground, wet soil, it all is important for seeing flooding. And the flash flooding typically is a result of training thunderstorms. So the ingredients in terms of meteorology, we typically will look for a slow-moving weather system, that prolonged rainfall in the same area, and the high moisture content of the atmosphere is always going to be favorable for heavy rain, and the combination of this again, during the summer months, we will see a very deep layer of moisture in the atmosphere combining with thunderstorms. That is going to produce the heaviest of rainfall. And as an example, in last July, we saw this in eastern Vermont. As you can see here, the very heavy rainfall is not moving very much over a long period of time. And so that's what results in flash flooding. And so we really, of course, a combination, just like all of our other hazardous weather, we look to see spotter reports to give us some ground truth in these scenarios. And we hopefully will provide the warning information and appropriately to keep people aware of the potential for flash flooding in these scenarios. And again, flooding is our #1 issue because it is so overlooked as being dangerous when you're out and about, and the power of water is as you can see in this fatality infographic on the left hand side, it's actually tends to be among all the hazardous weather, it tends to be one of the top causes of weather-related fatalities, and in particular in the North Country, it is our biggest concern given its impacts. So again, the idea that you are going to see changes very quickly with flash flooding, you'll have to react quickly, and in some cases you might need to seek higher ground where you hopefully won't be in a situation where you're stranded, but we'll want you always to get to higher ground as soon as you can, and just make good judgment to not travel into any kind of fast moving water, or even something that, again, looks like it's not terribly deep, but it doesn't take much water to knock you out or even sweep a car away. So to reiterate the impacts of flooding, also we want to highlight that it's particularly dangerous at nighttime, where it's very difficult to tell how much water is out there on the roadways, and therefore generally the rule of thumb is to turn around and don't drown. And here's another way of looking at it, where a washout can, this was reported by the Vermont Emergency Management, just terrible thing that can happen if you're in an environment that is seeing flash flooding, and you can have roads washed down and a car can be in big time trouble, like it was in this case. So that's all for flooding. We'll be coming to the last part of the presentation in a moment. Any questions? All right, nothing heard, so we'll move on to briefly talk about the hazardous conditions possible over Lake Champlain, and in relation to the marine forecasting that we do, we highlight the possibility of basically we put out a lake wind advisory, typically more often in the winter and fall due to instability. So basically, just like for thunderstorms, we're interested in how unstable the air is, and by nature of the cool water, relatively speaking, it tends to be more stable in the warm season because the water is colder than the air above it. So in addition to that, we are interested in the wind speeds that are going to be always higher than what they are on land due to the frictional, the difference in the lack of friction relative to the land surface. So again, over the stability is the key thing for seeing some of those stronger winds, and so those particular of interest in the fall season, when you still have warm air, and you'll see people, of course, out on the water because of how warm it is, how warm the water is, but now the air is getting relatively cold, and so therefore you see particularly strong winds during the fall season. And to highlight that with some numbers here, the graph here shows the frequency of wind gusts exceeding 25 knots and over Colchester Reef over Lake Champlain, and that really ramps up much more frequent in the fall season and in the early winter, and really comes down quickly into the spring and summer. And that idea of channeled flow is something that we also pay attention to, and is a factor for strong winds over the lake because of the nature of the Champlain Valley. The large-scale winds are kind of funneled north and south between the Adirondacks and the Green Mountains, and so this topographical influence is seen in the wind rows, showing the most frequent wind direction being out of the south-southwest or south during the entire year, basically, and with a northerly wind also occurring much more frequently than a west or an east. So just to show that idea in a little picture, and that will wrap up the talk with regards to our local weather. For your reports, we really want to see all the most important information, the where, when, what, and who are you, basically. We do know a lot of our spotters, but some of you who are new, we will not know, and so you'll need to provide us that information. So again, we want all those details, and we do have a handy form that you can find on our website to submit a storm report with all those details. And in terms of, again, the specificity is great. We want to know exactly where you're seeing that weather, and you can give us any kind of reference points that will help match us up with what we're seeing on radar, for instance, and when it comes to what we think is a possible severe storm, but we don't know exactly how strong it is. That can help us really big time. And so keeping in tune with what our forecasts are, I'm sure you are familiar with the NOAA weather radio, the alerts you can get on your phone. We recommend everyone having those in operation. And of course, you can always get alerts from media outlets. Here's an example of what the alerts should look like on your phone. We try to make it appeal specifically to your location when it's truly an emergency. So you won't see something for just a watch, but for something like an actual flash flood warning in a specific area, as this example shows. And as I touched on, we have a website. Our website does allow you to report any kind of storm report, but we are very much happy to take reports through other methods. Many people have shared, of course, on social media. We take those reports, amateur radio, by phone, and by MPing, which is a little project for a community reports of hail, and all sorts of reports can be shared via that application as well. And so basically can report anything that was discussed today, including tornadoes, water spouts, funnel clouds, severe weather with regards to strong damaging winds, heavy rain or large hail, damaging winds, even if you see lightning damage, not lightning, but if it's actually damaging something. Hail, and again, very specific. As I went over, there's different hail sizes that match up to common objects. So those give us a more specific information of how large the hail is. For flash flooding, we're interested in heavy rainfall rates if you are measuring rainfall, such as if you're part of a co-op or a COCO-RAS. We definitely appreciate those reports for special weather situations. Actual flooding is wonderful information for us, what we may not be aware of, and heavy snowfall and ice, of course, in the winter season. So with that, just to go over the general idea of why you are so important as spotters. You provide ground truth, and that ground truth can potentially save lives when we have that information to report with regards to wind damage or flooding, especially. We see all those different types of storms, and certain types of storms are more likely to produce severe weather than others. Our severe weather season is basically in the summer months, but it can happen in the spring as well, as we have seen. And of course, you should always keep yourself out of harm's way. And when you give reports, be as specific as possible, and that will help us to get the best information out to the public as possible.